Alright, hello everyone. Today we're going to be covering two different topics. One will be on the Tautochrone clock, which is perhaps an additional topic, and then we will dive into some properties of the derivative in multivariable analysis. So to begin talking about the Tautochrone clock, the idea for this shape came from the fact that one wanted to keep track of time at sea. And since there would be, rocking of the boat from the waves, a simple pendulum, circular pendulum, wouldn't work because sometimes it might go a little higher and then it might go a little lower, and then it would just be a disaster. But if someone found a curve that no matter where they are on the curve, it takes the same amount of time to reach the bottom, then it would be much easier to keep track of time on the sea. And so there would be, the idea was to create this Tautochrone curve. It's a very bad drawing. And there would be these sorts of bumpers. So the pendulum would sort of wrap around the bumper like so. And then that should theoretically allow it to keep track of time much better than that of a circle. So let's begin. Let's just go straight to the theorem. The inverted cycloid, which is described by this parametric curve, t minus sine t, cosine t minus 1, for from t is 0 to 2 pi, is a Tautochrone curve. So we want to discuss the following variables. T is our parameter. We have x and y, that's our position. S is arc length. And t, this will be time. So first we define arc length as we usually do, as the integral from t naught to t of the speed of the Tautochrone curve, differential of t. So first, if we take a look at the derivative of the arc length squared, that is equal to the norm of the derivative of the curve squared, and that is going to be equal to dx over dt squared plus dy over dt squared. So if you do the calculations for that, that turns out to be 1 minus cosine of t squared plus negative sine of t squared, which is equal to 2 minus 2 cosine of t. So remember that, I don't know if you guys are familiar with physics, but if you aren't, we're considering both kinetic and potential energy. So the kinetic energy, which is at the bottom, should be equal to the gravitational potential energy at the top. So we have that, v right there is going to be ds over d time, which is, if you do a little bit of algebraic manipulation up there, you get 2g times y naught minus y. So the single variable chain rule says that we have ds over dt equals ds over d time times d time over dt. Because remember, time and t are separate variables here. It might be a little bit confusing, but so what we can do is we can solve for d time over dt, which is equal to ds over dt over ds over dt, which is equal to the square root of 2 minus 2 cosine t over the square root of 2g y naught minus y. And if we plug in y naught minus y, let's see, over here, cosine of t naught minus 1 minus cosine of t plus 1. That gives us, in the denominator, 2g cosine t naught minus cosine t. And in the numerator, we have the same thing. So the time that we need to reach the bottom is t of pi, because we're going from t equals 0, or t equals 0, to t equals pi. Let me just clarify, that is the bottom, and that is the top. And if you put this in here, we get 1 over square root of g, the integral of t naught to pi, of the square root of 1 minus cosine t over cosine of t naught minus cosine of t dt. Now, the marvelous thing about this integral, and I'm going to box this, is that once you calculate it using perhaps Wolfram alpha, or if you're particularly interested in integral calculations, maybe you can do some integration tricks or whatever, it actually does not depend on t naught. So you have that t naught over here, you have that t naught over here. It turns out it is not dependent on that. And that integral evaluates to pi. So we have that the total time it takes is pi over the square root of g. So that is pretty interesting. We found a curve that it doesn't depend where you are. The time to reach the bottom doesn't depend on where you are. So that's pretty interesting. But that begs the question, what about the shape of the bumper? Because we have a Tautochrone curve, the inverted cycloid here, but what about a bumper? So at some point, at some point gamma of t, the pendulum is going to, the string of the pendulum is going to go straight in some direction, and then it's going to follow the shape of the bumper. So let's say we want to call this green curve beta of t. So we'll call this point beta of L, and we'll call this point beta of t. and we'll call this point beta of 0, which is equal to gamma of 0. And note, let's call this gamma of L, and note that the string should be, or if I drew it correctly, it should be pointing in the direction of, I believe, minus beta prime of t. So we would have gamma of t equals beta of t minus t beta prime of t. So that brings us to a definition. An involute of curve B of B is a plane curve G with parametrization gamma from 0 to L to R squared of the form gamma of t equals beta of t minus t plus lambda 0 beta prime of t. Similarly, we can define the evolute B of a plane curve G with parametrization beta 0L to R squared given by the following expression, which is the center of the osculating circle of G, gamma, forget of this prime. So it can be shown that over here B is the evolute of G, and over here G is the involute of B. But I'm not going to go through all that. I'm just going to go straight to the next section, which is on the derivative. So we are going to talk about a lot of things that are in multivariable analysis, and I'm going to be sort of rushing through a bunch of theorems that are necessary to understand differential geometry, but the proofs are long and tedious, and you could devote like a whole course to studying them on their own. So, suppose we have a function. Let's do that. Suppose we have a function from an open set U, which is a subset of Rm to Rn. We can break up f into its component functions, f1 dot 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 to fn, and furthermore, we have partial derivatives, fxi of p, which is equal to the partial derivative with respect to x sub I of p, which is the limit as t approaches 0 of f of p plus t. And remember, this is the part of the standard basis, minus f of p over t. Just like with parametric derivatives, you can compute these partial derivatives component-wise as well. So we have partial derivative of f1 with respect to xi of p dot 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 partial derivative of fn over partial xi of p, and that's basically that. Furthermore, if we take mixed partials, which is the derivative with respect to x sub I, and then taking the derivative of that with respect to x sub j, that is equal to, if you do it the other way around, first taking j and then I should note, before perhaps people start screaming in the comments, that this is actually this. Oh, that's pretty badly drawn. So even though the x sub I is to the left, we're still taking it first, because that's just the way the notation is for that. If we're using this notation, then the rightmost one is taken first. So we say that f is CR on U if all nth order partial derivatives exist and are continuous. And it's called smooth if it's true for all positive integers R. So let's begin with our first proposition. So if we have G from U, which is a subset of RL, to Rm is smooth on U, and F, which is from V in Rm to Rn, is smooth on V, and we have that G of U is a subset of V, then the composition F composed with G from U to Rn is smooth on U. So let's draw a diagram of this. So we have RL, Rm, and Rn. So let's say we have some. This is U, and let's say it maps onto this tiny thing. And we call this, oh no, that is not f of u, that is g of u. And we call this mapping G. And it is inside set V, and it takes us to f of V, and this is f. If this is smooth and this is smooth, then the composition f composed with G is smooth as well. So that's basically what it's saying. So let's go through another definition. The directional derivative of a function f in the direction v at the point P is denoted by dfp of v, which is the limit as t approaches 0 of f of p plus tv minus f of p over t, which is equal to f composed with gamma prime of 0, where gamma t equals p plus tv. basically, if we have a function that maps from Rm to Rn, and we have, say, like a straight line, and this is P, and this is V. Let's say F maps this to something like this. Oh, that's ugly. There we go. And say this is F of P, and this is the directional derivative. So it's the tangent line of the curve that results from taking the function of that line, that straight line. So there's also something called the Jacobian matrix, and it is basically the matrix of all first-order partial derivatives of f at p. So we have the Jacobian matrix is partial f1 over partial x1 of p dot 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 partial f1 over partial xm of p dot 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 partial fn over partial x1 of p dot 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 partial fn over partial xm of p. And that is the Jacobian matrix, and it is sometimes denoted as DFP. So this Jacobian matrix basically, I mean, it's pretty important, and you can see how it connects to the directional derivative. And we'll see later on that it's important in the context of tensors as well, but I'm getting sort of ahead of myself there. So instead of dwelling on that, let's keep going through these propositions. Proposition. Alright, sorry about that. My computer ran out of space, so I had to stop for a moment. So basically, what I was saying before is we have this proposition. So if we have a function from u to Rn, and it is smooth, and v is in Rm, and gamma is a regular curve, gamma regular with gamma 0 equals p and gamma prima 0 equals v, then the directional derivative is equal to this. So basically that's sort of what I was illustrating before. So there's also a chain rule, and that's pretty important. So since I think I'm close to running out of space still, I'm going to make this quick. D of the composition of f of g at q is equal to dfp composed with dgq, where p equals g of q. Moving on, one of the most important theorems in multivariable analysis, and I'm just glossing over it, which is kind of sad. Maybe someday I'll cover it in greater depth. The inverse function theorem. So, if we have a function from Rn to Rn, and it's smooth on a neighborhood of some point P in Rn, and DFP is an invertible linear transformation, then there exists a neighborhood U such that P is in U, such that V equals f of U is a neighborhood of f of P, and f from U to V is invertible with a smooth inverse. So the last thing I wanted to talk about is a diffeomorphism. And we have that subsets X in Rm1 and Y in Rm2 are diffeomorphic if there's a bijective function f from x to y whose inverse is smooth. And in that case, we have that f is called a diffeomorphism. Okay, I know I covered a lot of content today, but thank you for listening, and I'll see you in the next video.